Hello guys, so we are in lecture 8 of the bonus linear algebra section, and we're going to be looking at the matrix inverse today. So as usual, I've imported the necessary libraries, NumPy, Matplotlib. Sometimes wonder, why am I doing Matplotlib? Well, since I'm just getting used to this, isn't it? Well, really, we don't need Matplotlib.pyplot. But anyway, um, and I'm making my function, just the same function that we use to basically visualize the matrices in knife form. Okay, so the matrix inverse, what is it? Well, you all know about, if x is a scalar, if it's a number, we all know that x to the power of -1 times x gives you 1, right? I mean, we all know it. X to the power of -1, in other words, 1 divided by x, yeah? So that gives you 1. But this is a scalar, okay? Now, we can think of, oh my God, look at the pen. We can think of, a matrix A, okay, and a vector X and a vector B, because the inverse of a matrix is very similar to this concept, but there are some differences that you need to make sure that you pay attention to, okay? So just to elaborate on it, so if you have matrix A multiplied by some scalar giving you B, another scalar, okay? If you go and follow this basically, so the inverse of a matrix, I mean, don't worry about it, how you calculate it at the moment, just think about the inverse of matrix A multiplied by A. Now, obviously, when you do it on this side, you need to do it on the other side of the equation as well. So if AX equals B, then A to the inverse A times AX equals inverse A times B. We just basically multiplied both parts by the inverse of A. Now, the inverse of a matrix multiplied by the same matrix would give you the identity matrix I, okay? And I in identity matrix obviously being multiplied by, it's just like a identity matrix is like basically a diagonal matrix, all elements are 1, yeah? So really then X is going to be A to the power of -1, which is inverse of A times B, okay? So I just wanted you to make some, use your background knowledge, we have used, inverse of a number, multiplied by giving 1. So I want you to just realize that the inverse of a matrix multiplied by that matrix would give you an identity matrix, okay? There is important rules that you need to consider. So if you do a left inverse multiplication, then you need to do exactly the same thing. You see here, whether you put x minus 1 on this side or that side, that doesn't matter. But when you come with matrices, you really need to be paying careful attention. So we have 3 matrices. Let's say the dot product of matrix A and matrix B given matrix C. Then if we do a left inverse multiplication of AB, we need to do a left inverse multiplication on the other side, yeah? So this is correct, very important, extremely important, yeah? As a matter of fact, I really want you to take this message on board. You cannot do A minus 1, AB equals, C, then multiplied by inverse of the matrix. It needs to be left inverse, okay? And if you had it right inverse multiplication, then it needs to be on the right side, yeah? So very, very, very important rule. And just to, remember this, just, leave evil. So leave evil, that's reverse of the leave word, becomes evil, yeah? So if you have an A, B, C, 3 matrices, dotted with each other, the inverse of that entire dot product, basically, if you want to break it down, would be, just look at the order, and this is my bad, I should have put C, B, A. this is right now. Okay, so it would just follow the other way around. Yeah, so it would be C inverse, okay, multiplied by B inverse multiplied by A inverse. Okay, so this you can't do A inverse, B inverse, C inverse. It would be the other way around. Just remember, leave evil. So when you do this inverse operation, always, remember the leave evil. Same as, when you do transpose. Okay, but not all matrices can have are invertible. Yeah. So unlike, numbers, scalars that you can any number, you can, divide one by it, and you would have like inverse of that number if you call it inverse. Then that doesn't apply with matrices. Not all matrices have an inverse. They are only invertible if they are a square and if they are full rank. Full rank means not singular matrices, matrices which are linearly independent, and the columns are linearly independent. Yeah, so very important again. So two important points, or three important points that we just covered. Just bear that in mind. Okay, how do we do it? Now let's do this. Let's run this matrix. So we have the matrix A, which is 1, 3, 0, 1, 7, 7, 12, 7. Or we're gonna calculate its inverse, but is it full rank? How do we find out if a matrix is full rank? I'm going to use the simpy function, yeah, and from simpy I'm calling the matrix function sim.matrix A, okay. So basically this is a numpy array. Using the sim.matrix, I'm converting that numpy array type matrix into a simpy form so that I can use the reduced row echelon basically form. Do you remember this, guys? Let me just run this for you. Okay. And why am I calling 0 here? So that I can take the first section. Don't worry about this, yeah? All right? Because if I don't put the 0, I would be getting this whole entity. Whereas if I put 0 there, I'm just having the, output basically the reduced row echelon form, result coming up. Well, 1, 1, 1. Yes, it is a full rank matrix. Yeah, so it's determined that it is, okay? And that's what basically this code is doing. Okay, so yeah, now that we know that it is a square 3 by 3 and it is full rank because we performed the reduced row echelon form on it and it is full rank. And from lecture 7 with determinants, you remember if a matrix is not full rank, it will have a determinant of 0. Yeah, so obviously we know that we won't get a 0, we are getting 70. So that's another way of testing for whether the matrix is singular or whether it's full rank. Okay, and cool. So yes, this matrix is going to be invertible, and we do it with this function. The function is np.linealg. Sorry, np.linealg. Let me just run it separately before the function. So np.linealg.inv A would give you the inverse of matrix A. Okay, that's the inverse. And obviously I'm using the show function on the A inverse basically that I associated with this, just to like show it in a nice format. So very, very easy to calculate with Python by using the np.linealg.inverse function. Okay, and we said that, if you multiply the inverse of a matrix by it, it should give us the identity matrix. Okay, so if I do, A inv at the moment is the inverse of matrix A. So if I dot product A inv by A, I should get a identity matrix, and I'm going to run that, and I'm getting what am I getting? A is not defined. Why is it not defined? Oh, I do apologize. I didn't run this today. Okay. So yeah, and now run it basically, and a inv is the inverse of a. So if I go on dot a inv with a, yeah, so this is like performing this operation, I should get the identity matrix. And you might be like, oh, that's not identity matrix. There are numbers here, yes, but look at the power, 10 to the power of minus 16. Yeah, so that again is due to computer rounding errors, basically. So if I do np.round on it, it should basically get rid of these really, really tiny numbers. And obviously I would be getting the identity matrix. So yes, an inverse of a matrix dotted with it would yield the identity matrix. Now, if you want to do it by hand, I mean, obviously you never would, but just for the sake of practice, yeah, there is a method that you can do this by hand. And the way you do it is that you couple your matrix with an identity matrix. So you put them together, yeah. Let's say you concatenate A with I, identity matrix of same sort of dimension, and then you form a reduced row echelon form, and it would yield you, so if you couple these together and then you do reduced row echelon sort of process on it, yeah, then you would get a new matrix, which on the previous, on this section of it, which was associated with A, you would have the identity matrix, and this section, which previously was the I, the 1, 1, 1, 1, it would be the I inverse. That's how it's done manually. If you want to see how we do it, so show A, that's our matrix. I'm going to concatenate A, it's a 3 by 3 matrix, yeah? So I'm going to concatenate it with an identity matrix of size 3 by 3, okay? Along the axis I, meaning like here. If I don't put axis equals 1 here, so why don't we do that? I mean, if I was to do this, I'm gonna do it like that, 1, and obviously if I put 0, yeah, I would get that. So this is not what we want. We want it along the columns, yeah? So this is all I have done here. I had A, and I've basically concatenated an identity matrix to it. You see, 1, 1, 1. So this is A, yeah, this bit was A, and this is an identity matrix concatenated to it. And I'm going to now, because this is still a numpy array, I'm going to use the sim.matrix to convert it into a simpy type matrix, and I'm going to call the reduced row echelon form. We have done this before, so you should know why I'm putting a 0 here. I just explained it. And I should be getting exactly that, yeah? So look at that. What did I say here? So that when you concatenate it and you do a reduced row echelon form, you perform that operation, you will have identity matrix on where A was, and on where I was, you would have your inverse formed, yeah? And that's exactly what I have here, okay? So this section is now the inverse of matrix A. And then obviously you can then separate this out, with numpy slicing. Yeah, so I'm going to say temp equals np.array. Remember, the numpy array doesn't have a reduced row echelon form function. Yeah, so first I'm converting the matrix, this whole thing, into a simpy type to be able to do a reduced row echelon form. And then I'm calling the numpy the array on the whole thing to bring it back into numpy form. So that's what temp is basically. Temp is this in form of a numpy matrix format. All right. And what do I need from this? I need all the rows, but from column 3 onward. 0, 1, 2, 3. So from here, all the rows basically. And then that would be my manual inverse. Yeah, so if I do that and I show my manual inverse, I will have this. And we calculated A with the, we did it with, where did we do it? I deleted the function here, yeah? So we remember a in was np.lineage.inv, so using it through numpy lineage basically with the inverse function, or when we do it manually, which was the way I just showed you. And so this a inverse we had already calculated via np lineage in function. Okay, and we can see that yes, they are exactly the same thing. Okay, but obviously you will never go and do this in the manually. You can just use the numpy basically to do it for you. Now, another important, well, another interesting thing to consider. Imagine if you have a diagonal matrix. Yes, so I'm making dia equals np.diag of that array. So I'm giving an array to the diag function of numpy, and it will convert it into a diagonal matrix for me. So I have a diagonal matrix. We know that. And if I do an inverse of this, let's see what do we get. Okay. So to start with, we definitely agree that inverse of a diagonal matrix happens to be a diagonal matrix itself. Okay. Except that, how are these numbers calculated? Pretty simple. Okay. Look at that. Let's see. 2975. Hmm. Okay. Let's see. How is it working? I mean, just looking at point 0.5 and point 0.2 might give you a hint. What is 1 divided by 2? And what is 1 divided by 5? Obviously, I don't expect you to know what is 1 divided by 7 easily. 1 divided by 9, sort of. Yeah. That's all it is, guys. Yeah. So the inverse of a diagonal matrix is basically as if you get all those elements and get 1 divided by them. Yeah. So np.diag of this number is the same as this matrix, basically, is the same as the inverse of the actual matrix that had these numbers in the diagonal. Okay, so that should give you some hints as into how the inverse of a diagonal matrix is created. Well, again, it is very important. The inverse of a matrix is one of the most important concepts in linear algebra, which obviously, like if you want to discuss it, it takes you some sort of chapter maybe to talk about. But in terms of how you do it in Python, it's as simple as that. Well, I hope you have enjoyed this lecture, and I'll see you on the next one.